This is the third session we are continuing of the same content, that is vectors, right? And this is applied mathematics content as far as you all are aware of, right? So the topic is, you can get it down if you have a notebook, vectors. Topic is vectors, and vectors is the first lesson under applied mathematics. Applied math. Let's say applied math. All right. So you know that our first month, or let's say month of June, previously we were in the first lesson, that is modulus functions, right? Modulus functions. The good news is modulus functions has no relationship with this, as it was from pure math, right? So you don't have to worry about it. It was actually coming under pure math, so this is from applied math. So the, let's say, the intersection between the two lessons is like minimal. So there's no connection at all. Almost there's no connection. I mean, if you don't know modulus functions, I mean, it doesn't mean that you cannot learn vectors. Even without knowing modulus functions, you can learn vectors. So that is why, I thought of taking this challenge, because why I call it a challenge, most of the combined mathematics teachers, or even the school teachers, they don't teach applied mathematics until you come to a certain grade of pure mathematics, and that has been a common usage of most of the teachers. But what I think is that, yeah, Kavijay is asking whether this is 2023 or 2022. I mean, it doesn't matter whether you are from 2022, 23, 24. This is actually working for anyone, right? So technically speaking, if it is 2024, this is your lesson. If it is 2023, yes, this is your lesson. I mean, you can learn, but this course is specifically targeted for 2024. But still, we are actually, working on some advanced lessons. Usually they call it advanced, but it is not, right? Before the time that usually it is being done. So this is going to be a new experience, right? Because at the beginning, you learn something called vectors in physics. And if there's anyone from 2023 or 22 here, even, to learn this lesson, or even to just watch this lesson, so whatever the format it is, they would know that vectors in physics and vectors in mathematics is totally different. But in the beginning, people think that, okay, if I'm doing physics, if I go to a mathematics class, it's good because my physics knowledge would enhance, and it is not going to happen. And you know that, because in physics, what you learn as vectors, and in mathematics, what you learn as vectors is different. But you may wonder, what is that? But when you go through this lesson from the beginning, you will understand that, yes, there's a clear-cut difference, right? Okay, so let's get into the topic. When we are talking about vectors, we cannot just talk about vectors alone. We need to understand its basics, right? So there are a few beautiful basic concepts behind vectors, right? And can you raise your hands in case if you are not from maybe 2024, the people who has learned vectors somewhere in combined maths, okay? Vectors, anyone? You can raise your hands if it is yes. Anyone? Okay, we have one person, two. So two people, okay, three people who has learned vectors. Three people, okay. And please put your hands down. I think almost four people, right? So other people, they are new to vectors. But out of those people, is there anyone who has learned vectors in physics? So at least vectors in physics. People who has learned vectors in physics at least. At least ko hamara set karte na, wo combined math set ko physics wala hala thine, so you'd have learned definitely in physics, right? So at least physics, right? So we have another 4, I think it should be 8, right? So other people haven't heard of vectors so far. So there are 3 sets of students. You can see that some of them have learned vectors in combined maths, some of them have learned vectors in combined maths and physics, and some of them haven't learned vectors at all, right? So there are 3 types of students here. So just be attentive right? So that all these three levels will be delivered the same context, but you will understand in different levels for sure. So just imagine the term quantity, right? This is the first term we are going to use, quantity, to understand the basis behind vectors. Now you must be wondering why I am boasting about these vectors this much, right? I mean, the people who has done vectors, maybe they are thinking, right? So, but not that. This particular, lesson that we are going to start with, the concept called quantity, is going to have many marvelous applications in mathematics. I'll show you a small video that was on our WhatsApp group as well. But let me take the privilege to screen share it to you. Right, so it's a readily available video in YouTube and TED Ed YouTube channel. I don't know if you are fans of TED Ed. So let me get that nice video. And this is a very famous video. More than 1 million people have watched this. I don't know, few million people. Let me check that. Yeah, so it is been watched by more than 1.5 million people. So
physicists, air traffic controllers, and video game creators all have at least one thing in common: vectors. What exactly are they, and why do they matter? To answer, we first need to understand scalars. A scalar is a quantity with magnitude. It tells us how much of something there is. The distance between you and a bench, and the volume and temperature of the beverage in your cup are all described by scalars. Vector quantities also have a magnitude, plus an extra piece of information: direction. To navigate to your bench, you need to know how far away it is and in what direction, not just the distance, but the displacement. What makes vectors special and useful in all sorts of fields is that they don't change based on perspective, but remain invariant to the coordinate system. What does that mean? Let's say you and a friend are moving your tent. You stand on opposite sides, so you're facing in opposite directions. Your friend moves 2 steps to the right and 3 steps forward, while you move 2 steps to the left and 3 steps back. But even though it seems like you're moving differently, you both end up moving the same distance in the same direction, following the same vector. No matter which way you face or what coordinate system you place over the campground, the vector doesn't change. Let's use the familiar Cartesian coordinate system with its x and y axes. We call these two directions our coordinate basis because they're used to describe everything we graph. Let's say the tent starts at the origin and ends up over here at point B. The straight arrow connecting the 2 points is the vector from the origin to B. When your friend thinks about where he has to move, it can be written mathematically as 2x plus 3y, or like this, which is called an array. Since you're facing the other way, your coordinate basis points in opposite directions, which we can call x prime and y prime. And your movement can be written like this, or with this array. If we look at the 2 arrays, they're clearly not the same. But an array alone doesn't completely describe a vector. Each needs a basis to give it context, and when we properly assign them, we see that they are in fact describing the same vector. You can think of elements in the array as individual letters. Just as a sequence of letters only becomes a word in the context of a particular language, an array acquires meaning as a vector when assigned a coordinate basis. And just as different words in 2 languages can convey the same idea, different representations from 2 bases can describe the same vector. The vector is the essence of what's being communicated, regardless of the language used to describe it. It turns out that scalars also share this coordinate invariance property. In fact, all quantities with this property are members of a group called tensors. Various types of tensors contain different amounts of information. Does that mean there's something that can convey more information than vectors? Absolutely. Say you're designing a video game and you want to realistically model how water behaves. Even if you have forces acting in the same direction with the same magnitude, depending on how they're oriented, you might see waves or whirls. When force, a vector, is combined with another vector that provides orientation, we have the physical quantity called stress, which is an example of a second-order tensor. These tensors are also used outside of video games for all sorts of purposes, including scientific simulations, car designs, and brain imaging. Scalars, vectors, and the tensor family present us with a relatively simple way of making sense of complex ideas and interactions. And as such, they're a prime example of the elegance, beauty, and fundamental usefulness of mathematics.
Right. So if you notice, now they are talking very fascinating things about vectors, right? But I mean, to go up to that level, and even they're talking about things above vectors and scalars, it's called something called tensors, right? So you're not going to learn these things in advanced level, the tensors, but you will learn vectors and scalars up to a very good extent, where your logical brain will be mostly active, right? So quantity is a concept that we all know, right? But let me remind, if someone questions what is quantity, can you give me some answers? What is quantity? You can use a chat, you can turn on your mic and tell what is quantity.
Anything that can be measured.
Can you come again?
Anything that can be measured.
I can't hear you clearly. Can you come again, please?
Anything that can be measured.
Anything that can be measured. Were you there in one of our sessions before?
Yes, sir.
That's what. So don't help other people. So let's let them brainstorm, right? Anyone else? Now don't listen to what he just said. So you can come up with your imagination, what you thought. This is quantity. You can maybe type on the chat, or you can even tell by opening your mic. Anyone else? Because maybe what he just told is not correct. Who knows? Maybe it's just near to the thing that I am talking about, but maybe not the same thing. So you don't have to lose your courage. You can tell. Please. Anyone? Okay. Akesh is thinking something and anything that can measure is known quantity. Okay, that is Akesh's idea. So anyone else here wants to put your idea? Maybe this is quantity. Okay. No ideas. Okay. Aravind is thinking amount that can be measured. Okay. Amount is a different word. You can see that. So Akesh is telling that is something that can be measured. That can be measured. And Aravind is thinking that is amount of something, right? Yeah, amount that can be measured. So not of something. So that is amount that can be measured. Any other answers like that? So Aravind is thinking like this. You can see they are clearly different. Anyone else who has an opinion about what is quantity? Anyone? Because then we can continue. If there's no any suggestions, then we can continue. Can you raise your hand if you don't have any idea what is quantity, please? Quantity කියන එක දන්නේ නැහැ. ඒ මොකක්ද? The people who are thinking that you have no idea what is quantity. එහෙම කවුරුත් නැහැනේ. Right? Which means you have some idea, maybe you don't know how to express it. Maybe that's the reason. So basically, when you say quantity, it's about actually anything that you can measure. So the real definition would be anything that can be measured. Anything that can be measured. And amount is measurement actually. So quantity is anything that can be measured. So let me give you some lateral examples. Now, for an example, we have heard for some of the feelings, we try to emulate, the quantity, but it is not logical enough. For an example, if you tell someone, I love you so much, this so much part is wrong. You can say that I love you. I mean, that's a feeling. So that's the name of the feeling. Oh, that's a recognition of the feeling. But if you say this so much part, this is mathematically illogical. because love is not a quantity that can be measured, right? So it's not a quantity. So you cannot say that it's so much, right? This much. And I have heard this, some people say, now you are on the earth and there's this moon. I love you from the earth, moon to the back or something like that, right? So that's a length or a distance, okay? This is a distance. So, I mean, distance has a, magnitude. So you can compare, right? I mean, you can compare this with going to the Mars maybe, right? So if someone says, I love you this much, so that's a comparison. So someone loves you, like this. Yeah, I can see more examples. Light year, right? I mean, light year is also another displacement actually. So that's a vector. So love is not a vector anyway, right? So technically speaking, these feelings, not only love, sadness, right? Maybe caring, those kind of things, never use numerical, examples for that, because that is not true. If you use numerical stuff, I mean, most probably those people are lying. එහෙම කාටවත් කියන්න එපා මම ඔයාලට ගොඩාක් ආදරේ කියලා. හරිද? මොකද හේතුව ඇත්තටම එහෙම ගොඩාක් කියලා කියන්න බෑ ඒකට. ගොඩක් පොඩ්ඩක් කියලා එහෙම කියන්න බෑ. That is not a quantity, right? But quantity, සීනි කිලෝ එකක්. Quantity, no problem, right? මඤ්ඤොක්ක කෑල්ලක්. මඤ්ඤොක්ක කෑල්ලනේ මඤ්ඤොක්ක 500ක් gram, right? I mean, that is all right. So 500 grams of, let's say, brown sugar, right? Not that brown sugar, this, proper brown sugar, right? So technically speaking, all these things that we can technically measure are going to be physical things that is in my mind initially. Now, that is why this is always appearing in physics, because most of the physical things are measurable, right? I mean, if you have a table in front of you, you can check the length of that, you can check the height of that. So they have measurements. So everything that you can see and touch, so basically they have measurements. And there are few things you cannot even, see. But for an example, what you hear, you have a measurement, decibels, right? I mean, intensity of sound, intensity of light. These all are measurements. So you can see there's no difference. So all the things that you can see physically, that can be measured. That is for sure. So these quantities are maybe really existing in the nature, to be honest, to start with. But our course of study is not going to be physics. That is why I said from the beginning, we are going to move on a different path. Okay. First of all, let's get down this, definition. Write down, quantity is anything that you can measure. Quantity is anything that can be measured. That is much better. Quantity is something that can be measured. From here, we start the proper journey actually. So, quantity is anything that can be measured. Okay. Quantity is anything that can be measured. Please get it down. Quantity, right? Now, these things that can be measured are actually two types. Even though we thought all are physical, we have some of the quantities which are actually physical. These are physical quantities. Also, we have abstract quantities. You see, we have abstract quantities. We have abstract quantities. Look at this. When you go to physical quantities, you may notice that we have these kind of examples. Let's say we have distance, displacement, you see. Or you can have speed, you can have velocity, all right? So you may have, let's say, energy, and you can have moment of a force, right? You can have temperature, you can have pressure, right? You can have, let's say, intensity of light, you can have charge, right? Q. I mean, there can be a lot of, physical quantities like that, right? all these things can be measured physically, and I mean you can even have equipments, right? But abstract quantities, so let me give you a few examples. Abstract, which means it is only existing in your mind. All right, abstract quantities only exist in your mind. Example, real numbers. Okay, real numbers, it has quantities because you can actually distinguish them between the numbers, like 3 is bigger than 2, 5 is bigger than 1, likewise. So real numbers and complex numbers, right? Complex numbers will not only have a magnitude but also direction, because it is actually displayed on the Argand diagram. This is the imaginary axis and this is the real axis, and this could be a complex number, right? But real numbers, it has only numbers, you see, like 4, 5, right, 7. So moving further, you can have arrays, right? And you can have matrices, right? Imagine if you take an array, right? It can be a sequence, right? Or a combination of numbers, right? So on and so forth, right? So there's a doubt someone is questioning. So let's talk about it. So arrays, matrices. Now here we can have just linear arrangement of numbers, 1, 3, 6, 9, something like that. But matrices, they have eigenvectors. So let's talk about it, when we go to the last point of this lesson. So for an example, we have 1, 5, 2, 3. I mean, it can be directional and it can be actually represented on a Cartesian coordinate plane. So there can be, directions involved, right? Moving further, you can have what else? Any other abstract example that I can visualize right now? So we have real numbers, complex numbers, arrays, matrices. Okay, so we can have elements, sets, right? Because there are comparative figures, right? So I mean, these are quantities but abstract. Now you can clearly see there's one pathway. This is much more identical to this pathway, and here your physics branch starts and here your mathematics starts. So this is the difference between physics and mathematics when it comes to vectors. That is very important to know, right? So if there's anyone who's still thinking, let's say, abstraction of vectors in terms of physics, maybe that is an error point, that you cannot do questions in A-level condition when it comes to vectors, because you are thinking from physics and trying to do it from maths. It's not going to work. If it is maths, you have to think from maths, and that's the absolute of that, right? So basically this is mathematics, but you always use lateral thinking so that we can do applications of these things in physics for sure. But don't think from physics, because you will fall down, right? You will see a lot of mathematics come into the action after a while. So shall we get this down so that you can have a small note on different types of these quantities, and also write down a statement: physical or abstract, you can even call them virtual, but abstract is better. Abstract quantities do exist, right? So you can write down this quote and get down these examples and the environment that we are going to learn quickly. I'll give you like maybe 1 minute. So get it down quickly so that we are going to move on to our channel of, study area for vectors, right? So that is going to be the mathematical part of it, right? Okay, I'm waiting to erase this because we have a lot to discuss today, and I want to do it in a very calm manner so that will go slowly to your mind, so that you get this basis clear and understand this 100%, right? Okay, one guy is asking about time. Guys, since you're asking about time, time is very different. You cannot call it actually physical because there's no time, physically existing, because you cannot see time, you cannot touch time, right? So it's only in your mind, right? Your watch and my watch is just telling us a measurement, but it can be measured by a measuring equipment. So someone can tell it's still physical. So you can see, right? So it's resonating between them. It seems like physical, but it is actually not physical as well, right? So that is why we don't put them into one category. But I think when you learn physics, they consider time as a physical quantity. But in mathematics, we have to be absolutely correct. So we cannot put them into anything. And if you need to learn many things about it, you can read the book by Stephen Hawking called Brief History of Time. I'm pretty sure it's available on Amazon or whatever the other platforms available for books. You can read. That's a very nice read up. Okay, so let's continue. So let me get rid of this. I'm pretty sure that you all are done. Okay, write down. Tagal diya. Hadisi karan no ne paun. Right. Now raise the hands if you understand up to this particular point. May point in තේරෙන කට්ටිය අත උස්සන්න බලන්න ළමයි. There's no doubt whatsoever, right? වැඩේ දැන් තේරෙනවා මොකද්ද මේ කියන්න යන්නේ කියලා. Please raise your hands if you understand. That would be helpful so that I can understand that you understand. There are some more people who are not still raising their hands. Do you have any issue? No, right? බලන්න තේරෙන නැති කට්ටිය අත උස්සන්න ළමයි පට ලේසිය එතකොට. If you don't තේරෙන කට්ටිය. The people who can understand this up to this particular point, please raise your hands quickly. මහන්සියෙන් නෑනේ චුට්ටක් ඔය බට්නයක් ඔබන්නනේ තියෙන්නේ. Right? Aisha, Akesh, Janit, Sue, do you understand? Please raise your hands. Okay. Khabija and Janit, වැඩේ තේරෙනවද? Khabija and Janit. Kavija and Janit, you can always put a message on the chat so that, Janit is also good. Kavija, if you don't understand, please send a message on the chat with the doubt that you have, then I can start explaining from that point. Okay, so 99% understand the concept. So there can be physical and abstract quantities, where physical quantities are being analyzed in physics, where abstract quantities have been analyzed in mathematics. But we can always do applications from this abstract, not only to physics, but also maybe graphic designing, right? Maybe game designing, right? Or maybe, as the video said, air traffic controlling, right? Or it can be, miniature drawings, or it can be finance, right? I mean, there can be thousands of branches, where vectors has been applied, right? So that is why it is in applied mathematics. All right, so let's continue. So I'm going to get rid of this, and we are going to explore further in our channel, as I told you, the mathematics channel, right? So let's see how we are going to learn quantities from that particular point. So we are talking about abstract quantities, and I don't know whether you noticed, I always had 2 channels opening for every branch, which means there should be some secret, right? There is. Which means if you take quantities, now we are talking technically abstract quantities. So we have 2 main channels. One is scalars, and then we have vectors, right? We have scalars and vectors. And scalars and vectors commonly will have operations. For an example, scalars can be added, so addition is there. Scalars can be subtracted, so subtraction is there. Scalars can be multiplied, so multiplication is there. And scalars can be divided, so division is there, right? And vectors, yes, they can be added, vector addition is there. Vectors can be subtracted, of course. Vectors can be multiplied in 2 different ways. One is dot product, other one is cross product. So there's no division for that. We use both dot product and cross product to define division. Actually, division is actually a manipulation of multiplication, but technically speaking, you have 2 types of products when it comes to vectors. So now you can see there's a lot of mathematics we are going to use. So let's talk about scalars. Very simple. Scalars. So you would even tell me what is this? Quantities with a magnitude and magnitude only. You see? So here you will have magnitudes and magnitudes only, nothing else, right? So this is the literature of mathematics, very beautiful. So quantities with a magnitude and magnitude only. So basically here, since they are scalars, right? Since they are going to have only the magnitude, it is not going to have a unit like in physics. Now length, meters, units. So we don't have units, we have only the magnitude represented by a number. So 2 is a magnitude, right? Pi is a magnitude. Half is going to be a magnitude. It's just the size magnitude. You can compare them, right? Not only that, -5 is a magnitude, right? So you can see all these things are nothing but real numbers, isn't it? It's all about magnitude. So quantities with a magnitude and magnitude only. So we are talking about numbers, right? And if you apply that to physics, you can think about what? Distance. Distance has just a number. Only difference, since it's a physical measurement, it has a unit. For an example, 5 meters. Your 5 meters can be something like this. Let's say from A to B. There's a person who's moving, but direction always changes, right? So you cannot have some specific direction. So this length of this particular route is the distance, and that's a scalar because it is only a number. Let's say 5 meters, that's a number. Meter is a unit, and this is the quantity, isn't it? So that is a magnitude. So that is a quantity. It doesn't have any direction. For an example, you go to the grocery store and ask him from the uncle, මට සීනි කිලෝ එකක් උතුරට දෙන්න. එහෙම ගොම් පාට යන්නේ සීනි කිලෝ එකක් උතුරට දෙනවා කියලා ගන්න. You get my point, right? අපිට කියන්න බෑනේ මට මාළු 500ක් නැගෙනහිරට දෙන්න. Direction. I need let's say 1 kilo of red apples making 30 degrees of angle from 90, right? Utara means north, right? So from the north, making 30 degrees, give me 1 kilogram of apple. It's not going to work. But if you really want to think of its structure, it is actually moving towards down the direction, because weight is actually connected to the gravitational potential, but later we'll talk about that. But in simple, if you say in kilograms, it's not going to be the case, because it should be newtons then, right? So we are not going to go to that area. That is a little bit more deep into physics. But for the time being, at least we know that if it is only a quantity with a magnitude, then you only have the magnitude, and that is a number. Are we clear? If it is a quantity only with a magnitude, it's nothing but a number, a real number, right? The people who understood? All right, cool. So you can write quantities with a magnitude and magnitude only under scalars. So you can have 2, pi, half, -5, they all are real numbers. Strike R. So this is real numbers. Okay. Very simple. I'm going to erase this now. Moving further. So then what is a vector? Vector. What is a vector? Look at this. So if it is a vector, then it needs to have two properties. So I can write quantities with a magnitude and a specific direction. specific direction. Even if you just say direction, that is more than enough, because we can specify the direction later on. Okay, so quantities with a magnitude and a specific direction. So let's see. In mathematics, we use this particular shape or this particular shape to represent a vector. And this is called what? Can you just tell what is this? Okay, so what is this? Someone who can turn on the mic can tell. I'm going to draw it again. In mathematics, what do you call this? This shape or this shape? Maybe you can type. What is that for that?
Direction. Direction.
Direction. No, I'm asking what is the name of this symbol? What is the name of this symbol? What is the name of this symbol? You can even type. Okay, Rachita is thinking. Let me put everyone on mute. Mute all done. Dala apo mute all right. Yes, Karan. Okay. So basically, so you can turn on the mic if you only want. You can just either press the space bar or you can just turn on the mic, right? If you press the space bar, when you take it off, it gets unmute already. I mean, automatically. So this is actually called a directed line segment, right? So that is not an arrow or a parallel symbol. This is a directed line segment. Directed line segment. Directed line segment. Okay. And we use these two symbols for two positionings. For an example, this is the tail of the directed line segment. This is the head or the tip of the directed line segment. And when it is in this particular shape, most of the time we use a simple letter in boldface to recognize that. Simple letter in boldface. But I mean, you can't write boldface letters on a paper. So what you do is you underline. So this is another way of writing vector. But if it is in this way, most of the time you only put AB, so that you can write the vector as A, B vector. Are we clear? So you can see vectors can be represented with simple bold letters or by writing the segment and pointing the direction AB vector, right? So this is how we represent vectors. This is how we represent vectors. And if someone questions with what you are going to represent, don't call it arrow. Arrow can Yuddha Dipavachi. And there's a name of a TV series called Arrow. But here we are using a directed line segment, right? And that can be in two shapes. One, when you have a simple bold letter, but you actually underline to recognize, or a segment which is pointed towards the direction of this actual vector. Are we clear? Shall we get this down quickly, very quickly? So vector is actually vectors are quantities with a magnitude and a specific direction. At the meantime, it can be represented using a directed line segment. Are we clear? So we can actually use a directed line segment. Someone is asking, sir, can we say that this is an arrow symbol? No, there's no such thing called arrow symbol. There are arrow emojis, not symbols. All right. In mathematics, there's no arrow symbol, that is directed line segment. Okay. And you will understand moving further why we have to call it directed line segment. There's a lot of geometry to it, right? It's a very beautiful lesson. As I told you, you've been misguided by physics. So you have to unlearn that part and learn the real thing behind it. So now we know vectors and how it is represented. Very simple, right? And we know scalars and how they are represented. We have more to learn. So now if someone questions the magnitude of a vector, what is it? So magnitude of a vector is very simple. The length of the directed line segment. Directed line segment. Are we clear? So magnitude of a vector is the length of the directed line segment. Imagine if this length is L. Similarly, this is the same vector. So this is also going to be L. So you can write that is A. Something can be familiar. Modulus. Because modulus stands for the magnitude. Modulus stands for the magnitude. Nothing but the magnitude. Now the people who were there for the first month, they will be fascinated. People who are not there for the first month, still they will be fascinated because it is just a symbol, right? So this is AB modulus. That is also correct. AB modulus, you see, that is AB modulus. And this is same as in O-level geometry, the length of the segment is given like this, right? So there's a segment AB, so the length is AB. And also we can call the length was actually recognized as L, so that's going to be L. The people who understood this idea, the length of the directed line segment is nothing but the magnitude of a vector. So that is a magnitude. Are we clear? So magnitude is represented in many ways. Either simple bold-faced letter A, modulus, but since we cannot bold, we underline. AB pointed direction, this is also vector, so magnitude. And then this is equal to the segment AB, this is how we use in all levels. And finally, we just said that the length is L, so that has to be L, right? So shall we get this down as well quickly? Presentation notebook, right? Then you can always revise these things quickly. Complete magnitude, right? But to make the complete note here, I'll give you just one more sentence. This is very simple. Direction of the vector. So if someone questions what is the direction of the vector, so you may know at the moment we cannot actually say what is the direction because we don't have any reference. So we may just say this is DIRAO. You can call it DIRAB. Are we clear? This is just a notion. So you just say if it is a direction, that is DIR. So we haven't found any result yet, but yet we can call the direction as direction. This is the direction, right? But if we have Cartesian coordinate plane, you can talk about comparative to north, this angle, comparative to south, this angle. So basically you have learned such a lesson in all levels that is called bearings, right? From north, you are measuring the clockwise angle. So actually you are talking about the direction, right? But we are going to be more like detailing into this particular area, the direction of a vector. But for the time being, you know that magnitude of the vector is the length of the segment and direction of the vector is just represented by DIR AO, DIR AB vector, right? So complete it and we are going to move forward. Complete quickly. May idea up to here. So you understand the magnitude of a vector is given by the modulus notation, and that is the length of the directed line segment. And you understand, okay, there's this DIR notation for a vector to represent its direction after you find in any particular format, right? So this is just a representation, yeah. Sorry for the jabbering. So there is representation. Okay. Okay, let me get rid of this. Okay, we are clear. So let me erase this part as well so that our mind is also clear and I can brief it. So let's brief up to the point that we have learned. So brief. So far, we know that there's something called a quantity, right? And quantities are basically two types, either physical quantities or virtual or else abstract quantities, right? And then physical quantities can be two types. One is scalar and the other format is vector. Abstract quantities can be either scalars or they can be vectors. And the specialty here, this has units. And we are talking about something called measurements, right? So that is the physics part. So we don't need this. We don't need this. But this part we need because here scalars will have four types of operations: addition, subtraction, multiplication, and its variant called division. And vectors are going to have four such operations: addition, subtraction, dot product, and cross product, right? So you can see we are going to lead to some mathematical truth. All right. Scalars will only have a magnitude. So it is represented by real numbers. But when it comes to vectors, it has not only a magnitude, but also direction. So we will need a directed line segment this way or this way. So there are notions like if it is AB, you call this vector AB. Similarly, if this is named as A and this is also AB, you can write this is A in boldface and the magnitude. So it has two things. One is magnitude, and magnitude is nothing but the modulus of the vector. There is a notion, but that is the length of the segment. So if this is L, this is the length of the segment. Direction, we only have a notion for the time being, that is either DIR A, DIR A, or you can write this is DIR AB vector. So this is what we have learned so far. Shall we get down the brief quickly? Brief. So then your mind is also briefed. So we are writing the brief quickly. Get the brief. So we have come to the representation level of vectors. We have come to the representation level of vectors. Now we know with what we are going to play, right? Right? We are going to play with shapes. Right? Okay. Theory number one. Theory number one. That is equality of vectors. Equality of vectors. So we have the first topic today, or else the first concept today, right? That is equality of vectors. So let's see what happens if two vectors are equal. Now we are thinking in an abstract form. The physics part is not running in our mind, but if it is here laterally, it doesn't matter. So you have equality of vectors. So we are talk about two equal vectors, right? Something like this, right? So let's say we have this vector and this vector, they are actually equal and also parallel, isn't it? I mean, this is our mind map. So let's say this is AB and this is CD, right? And they are parallel to each other and also equal in length. So now we would say that in terms of the magnitude, they are the same, right? Because length is same. In terms of the direction, once again, they are same. You can see it is not even this. I mean, if someone writes this, they are different, right? But they are not. So they are identical, right? Because the code base or else the vector base is not defined. So you can state that this vector AB is equal to vector CD. So I can write if they are equal, then these things must be true. Number one, AB modulus is same as CD modulus, isn't it? AB modulus is same as CD modulus. Using all-level geometry, you can write this is same as AB being equal to CD, the length. Moving further, we can write AB is a parallel segment to CD. So that is second condition. You see, that is number 1, 2. And the third part, you can write direction of AB is similar to that of direction of CD. So this is third point, right? So we have AB being equal to CD, which means the length of the segment. They being parallel, and then their directions are mapping onto each other. So it is directed towards the same direction. So these are the three conditions. So we can write, if vectors are equal, first condition is that length of the directed line segments are equal. Number 2, they are parallel. You mean the line segments. And number 3, they are towards the same direction. They are towards the same direction. So these are the 3 points for a vector to become equal to another vector. So very simple, right? If 2 vectors are equal, then there should be magnitude equality. There should be directional equality, so that they are actually parallel to each other, right? So get this down. This is theory number 1, equality of vectors. So this is theory number 1, equality of vectors. Are we clear? So this is equality of vectors. Hari lasana, yeah? So we have some symbols coming up. So we are trying to roll the party. Let's see. Are we clear? Lasana karamu. Get the note. Okay. So far, how many of you understand? Better therena kattiya thosana balame. So vectors are equal under these 3 conditions. Tingala thosan, if you understand. Athosan again, just press the raise the hand button. That is more than enough, right? If you understand this, please raise your hands. Right? Cool. So this is the equality of vectors. So if 2 vectors are equal, then we can actually join the party. So let's do question number 1, right? And question number 2, right? And discuss about it, right? So if 2 vectors are equal, we know that at least they are parallel and equal in length. Also, they must be directed towards same direction. So with this knowledge, we should be able to start the first question. So I'm going to screen share the questions to you, Oshan. And I'm going to put myself under mute, right? And you can try question number 1 and question number 2 on this Level 1. Wait, Delilah. They are going to do some questions now. All right, I'm going to draw now. They are going to do a question, okay? So you have to do question number 1 and 2, very simple questions, but you have to be specific, okay? And you have to provide the proper reasons rather than just writing some random answer like a physics class. So we are talking about proper abstract vectors, not some bullshit physics vectors, okay? Physics teachers have kisi tarahan nahi mammi atalere gyan nahi. I mean, in physics, you learn the physics stuff because there are biology students in the class. So just imagine if they learn these kind of, proper, symbolic kind of vectors, they would definitely do agriculture from next day rather than staying in the biology class, right? Because if physics is going to be so advanced for them, I don't think that the bio students will survive, right? But math students, they need to have this advancement in their mind. And you can see this is not an advancement, this is a realization, isn't it? So vectors is a realization. It's very simple, right? If you just skim through the concepts, this is nothing but, the real truth behind how the physical things are existing, right? If you look at a video game, if you look at a graphic design, it's all dealt with vectors. And there you're talking about the arrangements, right? So there are a lot of nice things that you can do with vectors. So try question number 1 and 2 with consciousness and write the perfect answers. And if you're done with that, please DM me, don't send it to the group, right? And I will pop up this set of questions on the WhatsApp group once again, if anyone is using the phone, right? So that you can actually use the phone and open up the questions and do 1 and 2. Don't put the answers to the group, just put it as a DM, right? So 1 and 2, quickly. Find a mute, right? You can try. I'll give you like 5.5 minutes or 6 minutes. Okay, let's continue. So the very first question is about a shape that I really like, the hexagon. And you would have seen the people who has done Olympiad mathematics. Hexagon is the symbol for Sri Lankan Olympiad Math Foundation. And there are a lot of secrets behind this hexagon. Let's see whether we have time to discuss about them, but let's continue with the question. So we have a hexagon, right? We have a nice hexagon here. All 6 sides are equal. A cute hexagon. I'm just doing it on my hand, so it might not come that perfect, but I'm trying my best. Maybe you have these rulers and stuff, you can make it perfect. Right? So this is my hexagon. So I have these, vertices named by A, B, C, D, E, and F, right? So we have 6 sides, and all 6 sides are equal in magnitude and they are parallel to each other. So easily we can write vector AB is equal to vector DE, right? AB is same as DE, see, directed towards same direction. Vector BC is same as FE, right? Vector CD is same as vector FA, vector FA. Moving further, vector DE is same as vector BA, right? Vector EF is same as vector CB, and finally vector FA is same as vector DC. And if you notice, they are the opposites. See, now AB and DE and DE and BA. So this is later we'll call the reverse vector, but later we'll learn that. See, this is the reverse of this, and this is the reverse of this, isn't it? But actually there are 6 set of vectors, and looking at the question, let's see whether they are talking only about the sides or any vertex of the hexagon. Show me the question. Right. Name 3 parts of line segments which represents equal vectors. That means we have more. They are asking only 3 because they are not talking about what? The line segments where the sides are represented. It can be even this, right? See, it can be this. Vector EA, right, is same as vector DB. So we can write, we can have vector EA being equal to vector DB. Okay. And we can have vector FB being equal to vector EC, right? So vector FB being equal to vector EC. Not only that, we can have another variant, vector DF being equal to vector CA, isn't it? Vector DF being equal to vector CA. Similarly, they are reverse vectors. So AE is same as BD, and BF is same as CE. Finally, FD is same as AC, right? So all these shapes can represent vectors, but they are asking what pair of line segments or something like that, then it will slack down to another 6 only. Because even if you take the reverse, it's going to be the same thing. So there can be either 12 answers or 6 answers for this, but they are only asking 3. So writing down any set of 2 line segments will give you the answer, right? So this is question number 1. So can you raise your hand if you understand this? Can you please raise your hands if you understood this whole thing quickly? Question. Very simple. Very simple. Please raise your hands, Aisha, Akesh. Can you please raise your hands if you understood this part completely? Janit, Akesh, Aisha, right? Elagiri. So let's move on to question number 2. I'm pretty sure you don't need much time to get this down because it's a matter of picking just 3 line segments, set of line segments and putting them down. The next one is interesting. Seems like it's open in the logical brain and asking some, I don't know, literature question. I don't know. That you have to decide. And I have a doubt about your knowledge about these parallelograms because in the last 2 classes, many students gave some failure answers when it's come to this parallelogram. So let's see question number 2, how it's going to work for you. So question number 2 is a very nice question. It is asking about a rhombus, right? Before moving there, can you tell me rhombus belongs to which family? Someone, if someone can turn on the mic, can you tell me, yeah, which family? Abdullah, actually, I didn't hear you. Quadrilaterals. Okay, I vaguely heard you. Quadrilaterals is the big family member, actually. Right? That is a big person, right? Actually, there are 4 more family members there, if you really want to learn. Actually, we have 2 types to start with when it's come to parallelograms. Quadrilaterals are actually just 4-sided polygons, right? Quadrilateral means 4-sided polygons. 4-sided polygons, right? Right? So you know this, I mean lines, triangles, then all the other shapes are polygons, right? All the other shapes are polygons. So hexagon is also polygon. But this is specifically called quadrilaterals, right? And quadrilaterals can be either parallelograms or non-parallelograms. Non-parallelograms, right? So parallelograms, we have 4 types. Number 1, square, correct? Square. So when you kick the square, what do you get? Let's say you have a square and you kick the square. What do you get? Not the rectangle. When you kick the square, you get a rhombus, right? You get a rhombus, isn't it? On the result, just imagine what I'm telling. You have a square like this, you kick it, or kick like this. So you get a rhombus. Are we clear? And then we have the rectangle. And what is this? When you kick the rectangle, what do you get? You have a rectangle and you kick the rectangle. What do you get? Let me shape it again. What do you call this shape? Okay, I have parallelogram. Then mama කියනවා මේ ඉන්නේ මෛත්‍රීපාල සිරිසේන. දහම් සිරිසේන. මොකක් හරි සිරිසේන. ඒතර මේක සිරිසේන කියලා කියන්නේ. හරි අමාරුයි කියන්නකෝ. මහින්ද රාජපක්ෂ, ගෝඨාභය රාජපක්ෂ, නාමල් රාජපක්ෂ. එහෙනම් මේක අඩුමතර මේ ශශීන්ද්‍ර හරි බැසිල් හරි වෙන්න ඕනේ. Am I correct? So you can't call this parallelogram. That has a name, its own name. This is called the rhomboid. Rhomboid. In all levels, you would have learned this. බලන්න මේ දැන් සිංහලුත් නම් තියෙනවා. Square, සමචතුරස්‍රය. සමචතුරස්‍රය පයින් ගහුවාම එනවා rhombusය. ඍජු කෝණාශ්‍රය. ඍජු කෝණාශ්‍රය නෙමෙයි ඍජු කෝණාශ්‍රය. ඍජු කෝණාශ්‍රයට පයින් ගහුවාම එනවා මොකද්ද? රොම්භාභය. Right? So this is what I learned, I think, when I was in grade 7, right? I still can, have that in my mind, but I'm not sure why you are not. මේක අහලා නැති බබාලා කවුද ඉන්නේ rhomboid by any mistake? Anyone who දෙන්නෙම ඉන්නවනේ. The people who has not heard the term rhomboid before? rhomboid අහන්න නැති කට්ටිය 3 දෙනා 4ක් ඉන්නේ මේ පාර. මේ දැම්මම ගිහලා Google search පාරක් දාන්න types of parallelograms. Right? Types of parallelograms. You have to search and find what are parallelograms. Okay, non-parallelograms. So we can have trapezium, or in American English that's trapezoid. Right? You can have kite, and trapezium is where you have only 2 sides parallel to each other. And we have the kite where the adjacent sides are equal. මේකට තමයි kite කියන්නේ ළමයි හරි. නැතුව සරුංගලේට kite කියන අපි ආතල් එකට because the shape of the kite is like a kite and the kite is called sarungale, so we think sarungale is kite. That's the problem, right? Technically speaking, this is a mathematical shape and this is a dart and there is a concave, concave type of, what do you say? Yeah, concave quadrilateral, right? That's dart. And finally, we have the irregular quadrilateral, irregular quadrilateral, right? Which means it has no specific property. It is just like that. There's nothing special here. Are we clear? So we have 8 types of quadrilaterals. Out of that, this is my rhombus, and I mean you can even write this down if you want, or you can write this is know your shapes. Know your shapes. Actually, this is a kindergarten lesson, but unfortunately, there are some people who doesn't know these things, so you can write this down quickly. Know your shapes. So you have parallelograms and non-parallelograms, right? All right. Let's go to the rhombus straight away. Jump on, ready? So look at this rhombus. So look at this rhombus. We can see they are equal in length, right? But angles, only the opposite angles are equal. And all these sides are parallel to each other. I mean the opposite sides, sorry. Opposite sides are parallel. All these sides cannot be parallel. So opposite sides are parallel. So if I name it as, let's say, A, B, C, D, right? This is question number 2, right? So we can write first question. They are asking, what is the first question? Baba, first question. Okay, so they are asking, state with reasons whether the sides of a rhombus represents A equal vectors. Yes. First one is yes, but you can't just say can be. Why? Because there can be only when the sides are opposite. Only when the sides are opposites. Otherwise, they are not going to be equal vectors. For an example, you can have vector AD being equal to vector BC, right? Vector AB being equal to vector DC, and its reverse, vector DA being equal to vector CB, vector BA being equal to vector CD. So if you take only sides, they are going to be just opposite sides. So with reasons, now we have the result, part B. So part B is questioning, Oshan, part B is questioning whose vectors whose magnitudes are equal. Yes, there can be, right? Yes, this time all of them. Why? Because if you take the magnitude only, vector AB is same as the modulus of vector AB is same as modulus of vector BC. That is the magnitude. That is same as modulus of vector CD, which is same as modulus of vector DA. And you know there's no point of reversing because the magnitude is not going to change. The length, if this is L, all of them are going to be L. Are we clear? So that is question number 2 completed. Question number 2. right? Can you raise your hands if you understand this? The people who understand this second question completely, clearly, precisely, and clarity is 100%. Please raise your hands if you understand. Khavija, Abdullah, Faiz. All right. Cool. So number 2 is sorted. And we are moving to theory number 2. Theory number 2. We are moving to theory number 2. We are lazy, yeah? We are ona haraget karanna sinna. Oh, shall we try third question as? Shall we try 3? Quickly, karanna. Number 3. Screen share karanna. Taggal karanna. Some more recognition questions. So we have AP and PB. There are 2 line segments representing vectors P and. So you are more into symbols. So you are getting used to this symbolization under vectors. Question number 3. This is the very first day of vectors for you. So we started from the base, starting with nothing actually. Now we are reaching the symbolism behind vectors, and that is very simple to be honest. So we'll do it together maybe. So AP, so this is vector AP, and it says PB, you can start from the same point, PB. And these vectors are named as P and Q, right? Something like this. Or it can be this. I mean, another way of thinking around it, A, P on the same line, PB, right? That is also possible. But you can see the question is not telling something like that. I mean, this is also correct. But question is not talking about it. So, I mean, if you take it this way, you deliberately think that this is 180 degrees, right? I mean, that's a special case. That's called a special case. This is a special case, isn't it? Whereas here you don't know what is this angle. So this is like theta. So this is called a general case. General case. This is a special case or specific case, and this is general case. So I would go with the general case. But if they are talking about a special case, we can consider. So the first question says, if DIRP is similar to DIRQ, if they are equal, which means we are referring to this guy, which means they are directed towards the same direction. See, A, P and PB, they are on the same line, it seems. So I can write, then they are asking the relationship between AP and B. I can write A, P and B are monolinear, collinear. That's collinear, which means they are on the same line, right? They are on the same line, which is collinear, right? So I just work it out on the board while you are, looking at the question. Right? So you can see clearly that AP and PB, initially we thought it can be any angle, so that's why I came up with this. But the question says direction P is same as direction Q. So these two directions are equal, which means they are on the same line. So when they are on the same line, this is A, P and B, it's like this. Now when you are learning Sinhalese in your grades, I mean lower grades, you had these words to write. I mean, you have a sentence, but you have to write in one word, right? So for an example, ඕගොල්ලන්ට තියෙනවා ළමයි සිංහල වල මොනවද? ගල් වලින් හදන ලද ශෛලමය. right? Ratarang waling hadaneka swarnamaya. So if 3 points are on the same line, the single word will that is collinear. Collinear, right? That means they are on the same line. Second one is much more easier, I would say. They are asking what if the magnitudes are equal. If modulus P is same as modulus Q, isn't it? So if the magnitudes are equal, they are not only parallel but also equal in length, which means P is going to be which point? P is which point? Type you can type, you can talk. So what is this P? If two lengths are exactly equal. In the
Midpoint.
that's called midpoint. Very simple. So P is the midpoint. P is the midpoint of A, B. So that is also very simple, right? Okay. Moving further. So get this down quickly. I'll give you 1 minute. Very simple questions, right? Number 3, the people who understood number 3, no problem. Number 3, elagiri gompat, ona harageta bulu. Number 3, understood. Clean and clear. Then one, raise the hand bar. Number 3. Number 3. Number 3. Arne? Right, Maru. Let's move on. Arne? Abhisradayamu. Now we were talking about these different shapes. So let me take your mindset there a little bit. I mean, hexagon you know, once Archimedes tried drawing a circle inside this, okay, and outer circle, it touches the vertices, right? And basically this has 6 sides. So he moved on to 12 sides, then to 24 sides, then to 48 sides, and finally to 96 sides. You can see that you can double and change it, right? See, isn't it? So then this circle would come very near, right? This inner circle and outer circle would come very near. So more sides you have, they will be almost close, right? So then he used the longest distance between two vertices as the diameter. And then he was talking about this length, sum of the length as perimeter, right? Then if you take the perimeter and divide that by the diameter, all right, you get pi or approximations for pi. And if it is a circle, it is perfect because perimeter is the circumference and diameter still is a diameter, isn't it? So we know that C is given by pi d. Not only that, he approximated that pi is greater than 22/7 and less than 113 over other way around. 311/113, right? So this was Pythagoras approximation. That's why these days we are using in O levels we use 22/7. So hexagon is a very important shape. And you know, Archimedes also got killed when he was drawing some circles on the floor, right? But we don't know for what reason. Somehow, coming back to the point, today we started with the concept called quantities. And quantities were 2 types. One is physical, one is abstract. Let's not talk about physical because that's belong to physics. Abstract content or else abstract quantities that is going to be either a scalar or a vector. And if it is a scalar, it has only the magnitude, and that is represented by a real number. But if it is a vector, it has two more properties. One is the magnitude, other one is the direction, right? And when you're talking about vectors, we had to introduce the directed line segment and its notation, right? Simple letters, ball face, O, just the two ends, let's say the tail and the head. So we have vector AB as one notation and vector A as another notation. And the magnitude of a vector is given by the modulus sign. So that is A, O vector AB, O, you can even call that is the length of the segment if this is L, right? And direction is just a notion for the time being because we have no vector base so far. So direction of A is same as direction of AB. And we started learning the first theory, theory number 1. So theory number 1 says that these vectors are equal. So that is if vector AB is equal to vector CD, right? Then point, they are actually equal in length, geometry. They are actually parallel. Not only that, third point, I think there was a small disconnection quickly, but now we are back. Mom brief karapyo ke hamoda avanada people who are here. I briefed the whole thing up to this, right? Okay. Cool. So now we are going to learn theory number 2. Apoda calm down ela aathalle ki igana gonna theory number 2. Theory number 2. Balu moka theory number 2 kiyanne kiyala. Theory number 2. And this is a very nice one. This is vector addition. Vector addition. And note that this is just the beginning of vector addition. There's a lot more to learn. But we can still learn. Vector addition. One. When you add 2 and 3, you get 5. Am I correct? 2 plus 3 is equal to 5. 2 plus 3 is equal to 5. So, I mean, addition in scalar sense is a very simple process. You have real numbers. You have real numbers. And you have the process called addition. And then you get the sum. And that is also a real number, isn't it? You add any two numbers, let's say half and 1/3. I mean, you end up with, let's say, 5/6, isn't it? So you can see, you can add scalars without any issue because it has only a magnitude. The addition, subtraction, multiplication, division, all with real numbers, that is just a magnitude. So we have real numbers that can be added very easily, right? 2 plus 3 is equal to 5. Similarly, half plus 1/3 is equal to 5/6. But look at this vector addition process is going to be a little bit confusing because you can't put real numbers here. Instead, you have to put different directed line segments, isn't it? AKK. So this is addition, and your answer is not called the sum, instead it's called the resultant. And it is not a real number, it's again another vector, isn't it? When you add vectors, you are going to get a vector. So now you can see this is clean and clear. It is about adding the numbers, and this is what we were doing for 11 years so far. But this is something that we haven't done yet. So we will need to use lateral thinking to understand the resultant of two vectors. So let's use a case of a buffalo. Okay. Let's say there's a buffalo, right? in your house. There's this buffalo inside the house. බලන්න මේගොල්ලෝ අසන කතන්දර වලට. ගෙදරක් තියනවලු. ඒ ගෙදර ඇතුලේ ඉන්නවලු හරකෙක්. හරකා. I think someone wanted to screen share and show something. I mean, you can use the chat function, right? I mean, first you can ask the question and then I can, let you do that. So we can have this buffalo. And then, let's say buffalo is moving towards north, a distance of 300 meters. A lateral thinking, okay? This is not direct mathematics, 300 meters. So let's say the starting point is H, okay, home. And then the buffalo is moving towards east, and let's say that is 400 meters, okay, clean and clear. Let's say this is G, grass, tanakola kannane harakain, and this is the turning point. Let's call it T. Now, in the sense of vectors, technically, the buffalo has moved from H to G, right? Buffalo has moved from H to G. There be harakata කියනවලු. මේ හරකෝ ඔය ඇත්තටම බටේ ගිහලා තියෙන බොරු වැඩක් කරලා තියෙන, you could have gone this way. HG, right? Are we clear? Clean and clear, right? So this idea is called the resultant, right? And in this case, it's a very specific one. If this is 400, if this is 300, if this is 400, resultant's magnitude is going to be 500 meters, isn't it? But resultant vector is nothing but HG, right? So now we can understand, even if this is not going to be a specific shape like this, let's say we have a vector AB, okay, and there's no specific, angle. It can be anything. Let's say this is BC, but technically the resultant is defined from A to C, isn't it? Which means always the resultant is defined from the tail of the first vector. This is the first vector. So one after the other, and ends with the head of, or else the tip of, the second vector. This is the second vector, isn't it? So you may write AB plus BC is equivalent to AC. And sometimes teachers pick this point where B seems like disappearing, but I mean, these kind of kiddish stuff we don't need. It's better to know what is the real truth. So the vector sense is developed through this particular lateral thinking, right? So whenever you have AB plus BC, now you know that we are talking about AC, but we need to understand much more further. Up to here you understand. Vector addition simple scene. It's pretty geometric. Direct forward. We always start from the initial point or else the tail of the first vector. Then you end at the head of the second vector. Very simple. Patta simple. Tail of the first vector and then the head of the second vector. See, tail of the first vector and goes and finds the head or the tip of the second vector. When you connect them, that's going to be the resultant, and that is not called the vector sum. That's called vector addition, and there's no sum. That's called the resultant because that is another vector, right? But we need to still check whether your mindset is 100% clear. Okay, answer me. First point. Considering this, if someone states that vector AB modulus plus vector BC modulus is equal to vector AC modulus, is this correct or wrong? Make a hari kiyana kattiya dosan ba? People who think that this is correct. AB modulus plus B anarban wrong කියලා emoji එකකුත් තියෙනවා. Right? That's good. You have a reaction as wrong. I saw it for the very first time today. Right? So, if you feel like that, that is not correct, not wrong actually. Let me show you something. So let me come up with this AB plus BC concept again, because that is going to be vector addition for us moving further. So let me brief it this way. Now we were discussing on a lateral format. Now we are talking about the abstract format. Look at this. We have a vector AB. Okay. Any angle, we have a vector BC. Vector BC. From the very first point, or else the tail of the first vector to the tip of the second vector, we have the resultant. Therefore, we write vector AB plus vector BC is equal to vector AC. But similarly, someone can think that ABC are on the same line. We learned this collinear. Let's say vector AB ends here and vector BC goes up to here. So imagine if this length is L, if this length is M, and if this length is K. Okay. We know for a fact that M plus L is always bigger than K, right? Shishatri. That means sum of two sides of a triangle is always bigger than the third side, right? Sum of two sides of a triangle is always bigger than the third side. Right. So, if that is the case, we can write AB modulus plus BC modulus is greater than AC modulus. So there can be a lot of cases like that. But if it is this case, imagine if this length is X and if this length is Y, simply X plus Y is same as X plus Y. So we can write, for this particular case, vector AB plus vector BC is equal to vector AC. So looking at this, I think the correct statement should be vector AB plus vector BC is not equal, not bigger, but greater than or equal to AC, isn't it? Modulus of AC. Are we clear? So, vector AB plus vector BC is greater than AC when it is on a triangle, one after the other, and we have a specific or general angle. And if vectors are on the same line, which means all 3 points are collinear, the sum of the lengths is equal to the total length. So that is AB plus BC equals AC. So in general, this should be established, right? And that is why I started with a little bit of inequalities, because mathematics is a mixture of equalities and inequalities. But I don't know, for some reason, people always tend to equalities because they try to settle. But inequalities is the real truth, right? So when you actually combine them, you get a nice mixture. And this mixture is actually making mathematics beautiful. So if you think mathematics is all about equations, no, you are being misled once again. So inequalities is a nice friend. Api ආසයි මේවට. Inequalities එද්දී අපිට ආසයි දෙනවා. කැතේවට ආසයි දෙන්න ඕන. That is mathematics. ලස්සනේවට ආසයි දෙනවා නම් ඒ mathematics නෙමෙයි. That is art. I mean, art is also good, but always you go for the beauty. But here, the real beauty adds inequalities as well. Then the essence is nice, taste is nice, it's complete, right? Shall we get this down? This is vector addition for you. So vector addition has a geometric aspect and algebraic aspect. You can see that. The geometric aspect is merely because of the shapes and the directions that we have to use in terms of representing vectors. and the algebraic shape is based on its quantities and how it behaves in this geometric environment, isn't it? The people who understood how the vector addition works, vector addition වැඩ කරන විදිය දැන් ඇඟට තේරෙන කට්ටිය feel වෙන කට්ටිය අම්මට කිව්වේ vector addition is very simple because this is a feeling, right? Vector addition is a feeling, isn't it? Vector addition is a feeling. It is not a fact. It is not that someone can just say that this is it. This is a feeling. I mean, because this is much more natural. This is in applied sense. There are a lot of lateral applications here, so that you should feel it. And the mathematics behind it is very beautiful, right? Okay. So we know what is vector addition now, which means we can apply or start applying that to our questions. So get this down quickly. This is vector addition for you. And there are a few terms, catering this particular subject, like triangle law of addition because of this particular nature, and it works like a triangle. And also triangle law can be used to define a vector once again if there's something that behaves in the triangle law of addition, that is a vector likewise. And similarly, vector addition is extended to polygons, right? That is actually any polygon can be written as a combination of lot of triangles. So you can actually extend this and go up to the initial point and the final point connector as the resultant. I mean, that is you have seen in physics. But here in mathematics, we are not going to do those, Kirish stuff once again. But we will use the very basic or the fundamental triangular law and actually expand this content up to a great extent where you can solve many geometric things in your O-levels and many geometric things that was not in your O-levels using the concept called vectors and applications of vectors. It's a very nice and beautiful concept, right? So let me erase it. So we know vector addition now, vaguely or precisely. So some of you may have realized this by now precisely. Some of you may have a vague idea, but both can do. Don't worry about it. චුට්ටක් තේරුණත් ගොඩක් තේරුණත් තේරිලා අපි ගොඩක් තේරෙනකම් චුට්ට චුට්ට ඉගෙන ගමු. හරි. So let's move on to question number 4. බබා question number 4 දාන්න ඕෂා. දැන් එක ගැම්මටම කරලා දාන්න හිතේ තින්න එපා. Question number 4. It says AB is equal to PQ, BC is equal to QR, and that the points ACP are non-collinear. Show that ACRP is a parallelogram. Little sound like a geometric question in O-level, but you are dealing with vectors. If you can do this all alone, that means you are through, to be honest, right? Make a තනියෙන් කරොත් කවුරුරේ ටක් ගාලා WhatsApp group එකට දාන්න, which means you are the man of the day, man or the woman, I don't know. Right? So if you are done with this, do question number 4 quickly. ටක් ගාලා පොතේ ලියුවා, screenshot එකක් sorry. Photograph එක ගත්තා, දැම WhatsApp group එක ටක් ගාලා දාන්න. Let me see who does it faster than others. මුලින්ම කරන එක නමර බලන්න ඕනේ හරියටම තියෙන්න ඕනේ. diagrams තියෙන්න ඕනේ, explanations, notations, symbols. මේක පුළුවන් කියලා කියන්නේ වැඩක් තමයි. If you can do this question number 4 with this knowledge on the very first day of vectors, which means you are actually touching the advanced level sense at least, not the extent and the depth, but you are actually getting the sense of that. ටක් ගාලා කරන්න. I'll give you 2 to 3 minutes. Quickly do it. Put it on the WhatsApp group. Now you don't have to worry because this is the last session of the 3, because 9th we are not going to have classes because of these riots and stuff. So technically speaking, this is the last session of first lesson of vectors. ආපහු repetition එක ගන්න, right? අපි අඟහරුවාද දවාලේ කරා, අද බ්‍රහස්පතින්දා උදේ කරා, දැන් අපි බ්‍රහස්පතින්දා රැ කරනවා, ආපහු වෙනත් ඒව නැහැ, right? So quickly do this question number 4. ඉවර නැහැ, තාම පටන් ගත්තා විතරයි. the question says AB and PQ. So once again, we'll go for a general case. So we have AB and PQ. AB, the AP, AB and PQ. They're equal vectors, something like this. Say P, Q, equal in magnitude, directed towards same direction, and they are parallel to each other, isn't it? So AB and P. And then we have, so let me get this Q here so that it won't disturb our diagram. So I'm going to have BC is another vector, but the other vector should be equal to that. So it should be parallel and equal in magnitude. And there is Q, R. They are also equal vectors. So let's use our geometry knowledge. Equal in magnitude and parallel. Equal in magnitude and parallel. Equal in magnitude and parallel. So now we have a question to solve. That is AC, RP. And it is given that AC, RP are non-collinear. So of course it has to be a general shape, isn't it? Because if A and C are on the same line, you are not going to get this kind of a shape. Seems like a parallelogram, but we don't know how to show it. So it's a matter of understanding what is PR and AQ. So now definitely your mind says, okay, I know vector addition. So vector AB plus vector BC is vector AC, right? Vector AB plus vector BC is vector AC. Because our main concern is AC here, right? AC is the only. And vector PR. So vector PQ plus vector QR, vector addition, right? Vector QR is vector PR, isn't it? Vector AB plus vector BC is vector AC. Vector PQ plus vector QR is vector PR. But we have good news. Initially, it said that vector AB and vector PQ are nothing but the same. So let's call this vector as vector A. And vector BC is same as vector QR. And let's call it vector B. Good news. If you replace this notion, vector A and B here, it should reflect that vector A plus B is equal to vector AC. Similarly, vector A plus B is equal to vector PR, isn't it? Another one. AB is A, BC is B, PQ is once again A. Sorry, PQ is A. QR is B. So A plus B, and this is A plus B, right? So what we can see is, that both the vectors are identical. That is AC. So I'll write therefore vector AC is same as vector PR. Then it is all geometry. If two vectors are equal, we can write that their magnitudes are equal because AC modulus is same as PR modulus. So we can write AC is equal to PR. And since the vectors are equal, these segments has to be parallel. AC is parallel to PR, and this is nothing but the definition of a parallelogram, as long as they are inside a quadrilateral. See, this quadrilateral has opposite sides. So I can state that, but AC and PR are opposite sides of a quadrilateral. And you can write that. These are the opposite sides of a quadrilateral. So now we can state, therefore, this is a final statement. ACRP, the quadrilateral, where the opposite sides are equal and parallel. So is a parallelogram. That's a parallelogram, isn't it? So we have actually not solved but proved it. It is not a sum. So we would write QED. So you can check any past paper book. When something is proved, it is said that quod erat demonstrandum in Latin. This is meaningly, it is being proved. Quod erat demonstrandum. So when you prove something, don't put two lines. That is for a sum. If it is proved, either you have to put a square or you can write QED. But square is not used in local A levels most of the time. That's QED. So you prove that this is a parallelogram. It's beautiful, isn't it? So the people who think this is beautiful, can you raise your hand? This way of thinking into geometry using vectors, if you feel like this is beautiful, can you raise your hands, please? The people who think that this is beautiful, how you think through vectors up to the geometry that you already knew in a different world, maybe an abstract world. Akesh, what is the Tenuli, the people who feels like this is beautiful, you can raise your hand. Aisha and Tenuli, you think this is ugly? Because I don't see your hands. Or may I believe that you don't have that reaction button, or you don't hear me, or actually it's ugly. Please type it on the chat if you feel like this is not beautiful, because I need to understand why you feel like that. Because for me, this is one of the most beautiful applications that I see in the first time in my A-level life, and it should be same to you guys. මම A levels කාලේ මුලින්ම ආවම මේ geometry scene එක vectors වලින් කරනවා කියන scene එක මට මාර ආතල්, right? I mean, I feel really good about it. And if you don't feel good about it, I think you should go to maybe biology, commerce, art, something like that for sure, because this is the beauty of mathematics we are searching from the kindergarten maybe, right? So question number 4 is sorted. So we are pretty clear. Make a theory the people who understand this. The people who understand this without any hesitation. Patta. Right, cool. So this is the final step of the question. Quickly. Immediately. Lesson and complete. And before we do the next question, we'll do another briefing of what we have done so far. Then calm down. Brief. So let's see what we have learned so far, right? So let's brief it down. So you can write brief. We are going to brief what we have learned so far. Hello. We started with the idea called quantities and recognize that there are two variations. One is physical quantities and abstract or virtual quantities. Physical quantities are two types. One is scalar, other one is vector. And good news, we are not talking much about this because this belongs to physics. But we may use some lateral thinking to understand this whenever it's needed. And abstract, we have once again scalars and vectors. And scalars are nothing but real numbers. That's confirmed. We deal with numbers there. So it has operations like addition, subtraction, multiplication, and division, which is also part of multiplication, to be honest. And if you add, you get the sum. If you subtract, you get the difference. If you multiply, you get the product. If you divide, you get the ratio. But here, vectors are dealing with these kind of directed line segments. So there you have addition. You can have subtraction as a variation of addition, to be honest. But we have dot product and cross product, as I told you. There's no division, but division can be later defined as an inverse vector that we don't need at the moment, right? So moving forward, right? Moving forward, we learn few theories based on this idea called vectors. The first theory is based on the equality of vectors, isn't it? First theory is based on equality of vectors. And before that, let me remind the vector notation as well. That is also very important. So from the tail to the tip, we have a directed line segment, and it is named by the initial and the final points as a point of notation. And then with a simple bold face letter from A to B, right? And since we cannot write bold-faced letters on books, we use the underline. And number one theory, if vector AB is similar to vector CD, we learn that the modulus or the magnitude of one vector is definitely equal to the modulus or the magnitude of the other vector. Using geometry, we could write that the segments are equal in length. Similarly, since the vectors are equal, directions must map. Therefore, these segments are parallel to each other. And third special point, that the directions of these two vectors should map. So dir AB is similar to dir CD, right? So the directions are also equal. And not only that, we learn the theory number 2. We say number 2 here. Under number 2, we were talking about the vector addition. So when a vector is given as AB and then another vector as BC, the addition is from the first point of the first vector to the final point of the final vector. And this is vector AC. So AB plus BC is now equal to AC. And we just not finished there, we elaborated it little further, that vector AB plus vector BC is vector AC. But if you consider the magnitude, AB modulus plus BC modulus is basically greater than AC modulus. You can use it in 3 formats. I mean, one format is more than enough. And also we learned that it's a fact that, these kind of, applications are not only based on equations, but also inequalities, and that adds the beauty, right? And moving further, we will need this sense in terms of applications when it comes to vectors, right? So this addition sometimes gives you the feeling that the B is vanished. That is all right, but that is kiddish. But still, if you really want to use it, you can do that. And now we know that physics and the mathematics part of vectors is now in 2 different avenues, because we do applications moving on to mathematics rather than that of physics, but there will be some applications, right, for sure. Okay, so this is a brief so far. So we know vector addition, not maybe 100%, but we know vector addition up to a great extent now. And we know the equality of vectors. Only 2 theories, right? Only 2 theories we have done. Okay. Brief quickly brief. So the people who understood all the concept up to this point, right? So let me erase it now. And let's move to question number 5. Let's move to question number 5. Quickly attempt, give it a try for like, let's say 3 minutes, and then we'll start discussing. If you have done the question, right, put it to the WhatsApp group right away, right? වැඩේ හරිනම් group එකට දාන්න ටින් ගාලා ලස්සනට දාන්න. මට පේනවා සමහර කටි උත්තර වල දෙනවා කලිනුත් මරු. Right? So that speed is the most important thing. I mean, your mind should work faster than a machine. It doesn't mean that you have to be non-natural. It happens naturally. And then you become a master of it. So I want to make masters. I don't want to make, followers, right? The people who come to classes and, watch how it is being done and what is to be done. And that's called cookery, right? I always tell this in the classes that, from all levels, you do this wrong thing. Teachers are showing you how to do it and you learn how to do it. Then you learn only something called methods. Methods are there for cookery, for salons, like let's say hair designer, for armies, because you get instructions and then you play, right? So methods are good, but we use something called algorithms, right? In mathematics, you think logically. So those are algorithms. So it doesn't have to be, memorized. You don't need memory. That is my motto, right? All the time. Remember to forget and not to believe, right? So let's try question number 5. That is also very simple. And there's a lot of things to be understood while doing this question, right? Question number 5 is a very nice one. Take 3 minutes, then I'm going to discuss. So we are halfway through the set of questions as well when we are done with this. Right, so let's look at question number 5. Let's look at question number 5. Show me the question. Let's look at question number 5. Right. So we have RNS vectors. So we underline because we can't draw bold letters, whose magnitudes are 3 units. So initially we can write magnitudes of vectors are given. RNS is 3. Find the magnitude of vector R plus S. So they are asking the magnitude of the vector, which is the resultant, it seems. So R plus S. So let's say this is given by some L because it's a length. But you can see that they are asking for 2 cases. Number 1, if vector R is perpendicular to vector S, when they are perpendicular to each other. when R is perpendicular to S. When R is perpendicular to S. So they are asking what is this? L. So let me call this L1. Number 2, when the two vectors are making an angle of right or S, because you don't need the modulus to notify the perpendicular nature. Right. So let me erase that. Right. So when they are having an angle of 60 degrees, right? Let's call it L2. Right? So they are asking two lengths. So now we have actually sorted the question in terms of symbols. And let me explain it again and go for the diagrams. So question number 5 says, okay. Question number 5 says, okay, question number 5 says, we have vector R and vector S with a modulus of 3, right? And they are asking the modulus of R plus S, that we said that is L, but technically speaking, we have two variations of L. One is when this vector R is perpendicular to vector S. Second one, when this vector R is making an angle of 60 degrees with each other, right? So let's talk about this perpendicular nature. There are two ways that you can draw this. Number one, then our triangle law is not going to work because that's not one after the other. So we are not going to use it. Instead, we will use, this is vector R and this is vector S. So when they are perpendicular, this is vector R. So R modulus is 3 units. So this is the length. And this is also 3 units. And good news, this vector is the resultant. So that is vector R plus vector S modulus, or let's call it L1. L1 calculate L1 squared equals 3 squared plus 3 squared. This is 2 multiplied by 3 squared. So L squared is equal to 2 times 3 squared. Therefore, L has to be square root of 2 times 3, right? Which is same as 3 multiplied by root 2. So this L1 is equal to 3 times root 2 units. And you don't even have to write units because they are not physical. So 3 root 2 is enough, isn't it? L1 is 3 root 2. Now for this you can write that as a sum because we just solved that as a sum. When you have this shape, only you have this physics part called parallelogram of forces and stuff. So we are not going to do that. That is an application in physics, but this is the real part of mathematics. So part 1 is done. Simple enough to understand for anyone who has a simple brain of Sri Lankan O levels. Again, harak moleyat tibat make karanna puluwan. Sri Lankan O level pass wena gena harak ekkari. I mean, if you just pass Sri Lankan O levels, that means you are still in a very low level of understanding, like kindergarten. Okay, A levels is not that difficult, but it is broad. A levels කියන්නේ ලංකාවේ නෙමෙයි ලෝකෙම තියෙන පට්ටම ලේසි exam එක. A levels කියන්නේ පට්ට ලේසි. But it is not O levels. O level නෙමෙයි A level කියන්නේ ඉතර scene එක. O levels and A levels are different. මේකේ තියෙන්නේ ගොම් feeling එකක්, මේකේ තියෙන්නේ එන classical feeling එකක්. තේරෙනවද? දැන් O level කරනවා කියලා කියන්නේ නිකන් සිංහල movie එකක් බලනවා. A levels කියන්නේ තිය හොලිවුඩ් මූවි එකක් බලනවා නේද? දැන් මේකේ තියෙන අලි පැටියෝ ඔයයි මමයි. ටාටර්නේ. මේකේ තියෙන මොනවද? right? Multiverse of madness. right? හරි නේද? මේකේ තියෙන මොනවද? මේකේ තියෙනවා මහරජා ගැමුණු. මේකේ තියෙනවා Clash of the Titans. right? බාන්නේ වෙනසේ ෆීල් එකේ වෙනස. O level වල තියෙන මොනවද? තනිකර ගොබ්බ සීන් දෙවනි නියම. right? I don't know what others you have. I mean, very simple feeling. So I'm pretty sure that you are classical, fans when it comes to movies. So mathematics is classics, and that's beautiful. When you get it, you become a fan of it, right? So first part is done. So I'm going to need the space. So I'll just write the answer somewhere. L1 turned out to be 3 root 2. That is the answer for the first one. Second one, once again you think like that. See, if you draw it like this, that's going to make things complex. So 60 degrees, this is not the one we are going to use. Instead, we will use one going after the other. This is 3 units, vector R actually. This is vector R. And 60 degrees, right, good. So what I was telling, now we are coming to this part 2, where we have to solve a very simple question, that length of this part, given that this length is 3, this length is 3. So now we are talking about simple ordinary level trigonometry. There's this triangle where this side is y, this is 3. So I'm asking opposite over hypotenuse. What is it? Opposite over hypotenuse. Opposite over hypotenuse. Now you can hear me, right? Yeah, what is it?
Sine.
Yes, sine. So angle is 60, so sine 60. Someone tell me what is sine 60? Sine 60, what is the number? Sine 60 is, what is that? Root 3 over 2. Yes, I saw that on the chat. Sine 60 is root 3 over 2. This is ordinary level. Huh? So y value is equal to 3 multiplied by root 3 over 2. So y is sorted. Similarly, we can write x divided by 3. See? This is x. So adjacent over the hypotenuse.
3.
Is equal to cos 60, right?
3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3. 3.
And cos 60 is simple, and that is half ordinary level mathematics. So x is equal to 3 over 2. I think game is. So let me erase this and write a very simple diagram now, because we know a lot of values. L2 is unknown, right? And this is 3. And this value is found, and that is y. Y value is 3 root 3 over 2. And this value here is simply 3 over 2. So we can do a small simplification and finish it off. All level print, nothing in A level. See, you can write L2 squared is equal to square of this, that is 3 root 3 over 2 whole thing squared. 3 plus 3 over 2. 1, 3 plus 3 over 2 is same as 9 over 2, right? 1, 6 plus 3, 9 over 2. So 9 over 2 whole thing square. 3 plus 3 over 2. So moving forward, so this is 9 multiplied by 3, and 4 is the common denominator, plus 9 multiplied by 9, isn't it? So we can take that common 9 out. That will give you 3 plus 9, that is 12, divided by 4. 4 times 1, 4 times 3. So we get 9 multiplied by 3 as L2 squared. So you can write L2 squared is equal to 3 squared times 3. Therefore, very simple now, L is equal to 3 times root 3, right? Isn't it? You can write units, or you can just leave it, because that is the final answer. And we need just abstract solution, that is 3 root 3. Are we clear? Question number 5, part 1 and 2, very simple, right? All well past right? This is very simple. Nothing special in mathematics. People say that we need a lot of trigonometry for vectors, not really, right? This is about understanding. When we go to applications, we can actually apply rapidly. This is the very first day of learning vectors, right? There's a complaint about my sound. I mean, because I just changed the mic. So is there any problem still going on? Sound is older? That seems like. But can you at least hear me? I mean, can you at least read me? Because I can't understand. Because there's one person who said that sound is not really good. But I mean, if you can hear me enough, that's more than enough. Because, yeah, I mean, if you can hear me precisely, that's more than enough. Clear, right? Okay. I'm really sorry for that. I mean, our guys would have been more responsible in terms of these mics and stuff, because knowing that there's a night class, they have to make the things ready. But unfortunately, I had to use this low quality mic, for the last few minutes of the class, and I apologize. So let's clear it off. Now you can take off your pens and pencils and everything out, right? So we are going to finalize the day. So we started. So this is the final brief of the day, and we are going to finish. And this brief is in your mind. We are not going to write, and I'm also not going to use the board. So we started with the concept called vectors, but the thing is, to understand vectors, we wanted the concept called quantities. So quantities are the things that can be measured. So love is not a quantity because it cannot be measured, right? So sadness is not a quantity because it cannot be measured. So those things are most of the time feelings, right? So the things that can be measured are two types. One is physical, one is abstract. Physicals are two types, vectors, scalars. Abstract, two types, scalars, vectors, same thing. Okay. But the physical part is studied through physics and the abstract part is studied through mathematics. Under mathematics, we started the concept called vectors and scalars by giving the idea of the scalars, which is only a magnitude. It is always represented by a real number. And then a vector is represented by a directed line segment. And this directed line segment is usually named from the tail to the head. And the capital letters with a directed pointed, this arrow shaped thing, but it is not arrow because it is called a directed line segment, right? And this one can be also defined using a simple bold letter, but usually we cannot bold when you are writing, so we underline, right? And that is how we represented a vector because it has a direction and a magnitude, but the scalars, it will have only a magnitude. Plus, scalars have operations like addition, subtraction, multiplication, division, but that is just a quantity, isn't it? And that quantity has only the magnitude. But this part is different when it comes to vectors, so we cannot use addition in that way. So first we learn the theory of equality for vectors, where the vectors are being equal such that the segments are equal in length and segments are parallel to each other and they are directed towards the same direction. And then when the vectors are actually added, it is actually defined from the initial point of the initial vector to the final point of the final vector, or the tail of the first vector to the head of the second vector, and that is called the triangle law of addition. And then this particular vector addition we used to understand some geometric existences, right? So basically, the geometry that you learned in O levels and the geometry that you haven't learned in O levels all can be analyzed using this beautiful concept called vectors, isn't it? But moving further, you will have two aspects of vectors as well, Marune. When you go to vectors, moving further, you will have vector geometry and vector algebra. But good news, they are not separate. They are always playing the game together. So that is a nice thing. So it is almost like analytic geometry. It's almost like Cartesian coordinate system. It's almost like coordinate geometry. And when the Cartesian coordinate geometry connects with the Argand plane, the complex numbers will also behave like vectors. So vectors is a long journey that we have to travel. As I told you, vector operations are not just addition, subtraction. I mean addition and adding the reverse vector, something like that. But it has also products like dot product and cross product. So let's see what we are getting into. And you have 5 more questions as your homework for the first week. And I will send that same note to the WhatsApp group again. And you can notice there's one nice question. I think question number 7, I can remember. You have to prove the midpoint theorem. Right? So you have to prove the midpoint theorem. O-level theory, right? Midpoint theorem. And there are lots of questions, right? So basically, you have 1 week off. That means next week is few days away, 7 days, right? So this 7 days is more than enough for 5 questions. Per day, per question, 2 days off. You can actually, make it a reality. But I need you to do all 10 questions and make it one PDF and send it to me. Now maybe on the WhatsApp group itself, because there's no problem. I mean, if you want to send it DM, that is also all right. Group DM but you can discuss among, right? You can discuss and do it nicely. Do all 10 questions and DM me and tell me the people who thinks that they are all clear with vectors done so far. Others and the people who feels like you are pretty cool about what we have learned so far. Very good, very good, very good, very good, very good. Right. Okay, so we are actually done for the day. And if you have any comment about the lesson that you learned today, you can use a WhatsApp group for that. And you really know that I appreciate, your comments, because I feel like, doing the classes much more further. And I feel like, inspiring myself when I see your comments and stuff. So I really like that. So whenever you are done with the class, whatever the comments that is coming to your mind, even if you want to scold me that this bug is doing something like that, I don't like it, you can put it to the group, no problem, because I'm open for commenting, suggestions, complaints, or even if you feel like there's something creative that we can add during these series, you can always let me know. Okay, then I'm going to finish it off. Do all the homework and send me the PDF. Next week, we will start from the midpoint theorem and the applications of vectors. And if you see the beauty that we start from very basics called quantity, a very simple idea, and we develop up to vector addition, and now we are applying that in the past geometry in a modern way, right? So there are a lot of applications of vectors coming up. It's going to be much more beautiful going further. So do your research, Google the things that I said, and make your mind available for the next week. All right, then good night. Have a nice day, nice week. And I hope that you will send me homework fast as possible. Okay, then bye.